Hello, my name is Steffen Polzer and I'm going to talk about the functional central limit theorem for Polaron path measures. This is joint work with my advisor Volker Beetz at TU Darmstadt. We consider probability measures of the following form. We take a distribution of a d-dimensional Brownian motion started in -t and perturb it by a pair potential of this form. Here W is positive, measurable and point symmetric in the space variable. The coupling constant alpha determines the strength of interaction, and the partition function z is a normalization constant. Consider, for example, this choice of W here, which leads to the path measure of the Fröhlich Polaron. Then we have a self-attractive interaction, so paths with increments that tend to be small get rewarded. Our goals are, first of all, show convergence as t goes to infinity, and then show in infinite volume that under diffusive rescaling we again converge to a Brownian motion. For the Fröhlich Polaron, we would expect the respective diffusion constant to be smaller than 1 due to the self-attractive interaction. Due to the translation invariance of the potential, we can't expect the distribution, for example, of the function value in 0 to converge. And we will look at all of these measures on the sigma algebra generated by the increments. We have a short look at the path measure of the Fröhlich Polaron. The system one is interested in is an electron moving through a crystal. The electron tracks a cloud of polarization along, and this leads to an increase of the effective mass of the electron. The path integral formulation of Feynman leads to path measures of the kind introduced earlier, where W has this form here. And this probabilistic formulation was used in 1983 by Donska and Varadan in order to prove a conjecture by Picard, which states that minus the Cronstedt energy grows quadratically in alpha, where this constant G0 here is given by variational formula. In 1987, Spohn conjectured that under diffusive rescaling, paths converge to Brownian motion, and then the inverse of the respective diffusion constant is the effective mass. Recently, it was shown by Mukherjee and Varadan that for small alpha, the path measures converge in a suitable sense, and that the increments converge to Brownian increments on a diffusive rescaling. We extended the results of Mukherjee and Varadan to all coupling constants. We extended the behavior under diffusive rescaling to the whole path, so we showed a functional central limit theorem, and additionally, we modified the approach of Mukherjee and Varadan, which used in many steps the explicit form of W for the Fröhlich Polaron in such a way that more general W can be treated. We assumed this growth condition here on the partition function and showed that first of all we have convergence of the measures locally in total variation, and second that if we additionally assume that W is quasi-concave in the space variable, which means that superlevel sets are convex, that under diffusive rescaling we have convergence to Brownian motion. The full versions of these theorems additionally contain more or less explicit formulas for the infinite volume measure, as well as for the diffusion matrix sigma, and we also give examples when GC holds. The growth condition is rather natural because it basically means that if we take the interval from -t to t and cut it in half in the origin, and then suddenly forget all interactions between the left and the right hand side, that this effect stays bounded as t grows to infinity. For the Fröhlich Polaron, the partition function can be written as a matrix element with respect to the time evolution operator generated by the Fröhlich Hamiltonian at total momentum 0, and here omega is the Fock vacuum. And in 2020, Dybalski and Spohn showed that this Hamiltonian has a unique ground state, that it's non-orthogonal to the Fock vacuum, and application of the spectral theorem then yields that the partition function grows exponentially with t, which means that GC holds, and thus our results are applicable to the Fröhlich Polaron for all coupling constants. Our starting point is a modification of the point processor representation introduced by Mukherjee and Varadan for the path measure of the Fröhlich Polaron. We fix some probability density G that is strictly positive and has a finite first moment, and define finite measures mu alpha t as it's done here. And additionally, we factor out G from W to obtain this function V here. If one then expands the exponential into a series and interchanges the order of integration here, then one obtains this equality here. And now we look at this series over integrals here in terms of an expected value with respect to the distribution of a Poisson point process with intensity measure mu alpha t, and obtain this equality here. We now take the identity derived on the previous slide and normalize the inner expression by introducing some normalization constant depending on the point configuration. And then we can see the inner expression as a probability measure in dependence of this point configuration evaluated at the event A. And of course, we have to reweight the distribution of the PPP outside and obtain this reweighted distribution here. If we now want to show the convergence of the path measures, we need to show convergence of these distributions here. And this is done by identifying some sort of renewal structure and then applying renewal theory. We start by having a closer look at these distributions here. We identify a point configuration here with a collection of intervals, and we look at the following way to randomly generate such a collection. We draw the left interval points according to a homogeneous Poisson process with intensity alpha, and we draw the interval length with density g independent of each other and independent of the left interval points. Then we have alternating dormant periods, which are not overlapped by any interval, and active periods here. And we have embedded renewal process after which the system regenerates. And we will call the length of the first renewal period here T1, and we call the first cluster of intervals here Xi1 and its distribution by Xi alpha. And if we now translate this process by minus t, and say, for example, here is t, and condition that we are dormant at t, then this process from minus t to t has a distribution gamma alpha t, so the distribution here. And now, of course, we're interested in this reweighted distributions here. And first of all, notice that this function f here is multiplicative in the clusters due to independence of Wiener increments. And at least for the Fröhlich Polaron, this reweighting should have the effect that clusters get denser. The condition of Mukaye and Varadan is now the existence of a parameter lambda such that this first expected value is equal to 1 and such that this second expected value here is finite. And then this reweighted distribution here can be obtained by simply reweighting the distributions of dormant periods and clusters. So this means if we change the distribution here of the dormant periods and reweight the distributions of clusters here in a suitable manner, then and then take the process from minus t to t, conditional on the event that we are dormant at t, then we obtain this reweighted measure gamma hat here. And then an application of renewal theory yields convergence of these measures here to stationarity in a suitable sense, which yields the existence of an infinite volume measure for the path measures. This, however, leaves the question how to deal with this condition G. We have shown that our growth condition GC is equivalent to the condition of Mukaye and Varadan, and it might be worth mentioning that GC is also very natural in this point process setting, because one can easily show that GC is equivalent to the probability under this reweighted measure that we are dormant at 0, staying bounded away from 0 as t goes to infinity. These measures here have also some kind of product structure, which basically means that we can draw the processes or increments independent of each other along these reweighted clusters, which then yield with the renewal theory and the Gaussian correlation inequality the functional central limit theorem. The quasi-concavity was needed for the Gaussian correlation inequality, which was mainly needed for tightness. If we take here A to be the whole space, then this equality here yields the partition function in dependence of the Poisson point process, and some additional minor calculations then yield this equality here, where here we have a contribution for any cluster that falls into the interval from 0 to t. And if we now distinguish between the two cases that we either have a renewal before t or that we don't have one, we obtain this renewal equation down here, which is in general not with respect to some probability measure, because the expected value of f of c1 does not have to be equal to 1. And the trick from renewal theory is now to multiply such an equation by exponential, and we then obtain these equations here, these renewal equations here, and we now looked at the limiting behavior of the solutions in dependence of the parameter lambda, and obtained that indeed the condition of Mukherjee-Varadan is equivalent to our growth condition, and in this case the unique solution to G is given by psi of alpha minus alpha, where psi of alpha is the free energy. The fact that psi of alpha minus alpha is the unique solution to G can be used to derive interesting identities for the Fröhlich Polaron in terms of the reweighted point process. So for example, alpha times psi prime of alpha is equal to the expected number of intervals in the reweighted cluster divided by the expected length of the reweighted renewal period. If you are interested, you can find our preprint on archives. Thank you for your attention.